determine the number of state variables and as well as we have to find out the state variables parameters. Okay. We have to look at the d over dt term. So this is 1 d over dt. That means this will be our first state variable, right? So the state variable is inside this state vector x. So as this is second order system, so we have two state variables for this x. So the first one is, let's say, x1, the second one is x2. So what is x1 here? x1 is the del delta, because this one is the first state variable, right? And what is the second state variable? Here we can split it like this, d over dt, d del delta by dt, right? So this one is our second state variable, d del delta over dt. Okay. So this thing has been written over here. x1 is del delta and x2 is d del delta over dt. That is again the x1, right? The first derivative of our del delta. That we can represent it by del omega, the small change in the angular velocity. After that, we have to find out the x dot, that is the x1 dot and x2. Okay. So from this line, we can easily write that our x1 dot is nothing but the x2. So this is actually the x2. Okay. And the x2 dot we have found out here, right? So x2, what is x2 dot? It will be d square del delta over dt square, that is this term. So these two terms we have brought it to the right side, so it will be minus this and minus this. Okay. Now again this term is the x2 and this term is x1. Okay. So what will be our x2? It will be simply minus pi f naught t over h x2 minus pi f naught ps over h x1. That means we have to represent the x1 dot and the x2 dot somehow in terms of x1 and x2. Then we can write these two equations in matrix form. Okay. And we have to use this expression, x dot equals to ax plus b. Okay. So this is our x dot, which will contain x1 dot and x2 dot. Then this is x, we know this thing. Now we have to look at these two equations, that x1 dot is x2. That's why this first element is 0 and second element is 1. Okay. And to make x2 dot equal to this thing, we have written, look, with x1 this term has come, right? So here this thing for x1 and the second term will be multiplied by x2, so that we can get this thing. Okay. So this is our A matrix, this is x. And we saw that we do not need any class PU term here, right? That means we do not have for this system. And in this case, our expression is like this. X dot equals to only ax. This type of expression is called homogeneous state equation or unforced state variable equation. Why unforced? Because there is no input or forcing function acting into this system for this case. Okay. Now we will proceed. So what was our target? Let's go back to our target. Otherwise, it will be lost. Okay. So actually, why we are studying the statistics modeling? Because previously, okay, look, this was our linearized equation in time domain. Okay. Then we applied the Laplace domain, and it is now in the frequency domain. We divided del delta of s from both sides. That's why this term actually got vanished. Okay. Then we actually found the solutions of s. Okay. S is the root of O. Then we actually placed those roots on the S plane, and depending on the root location, actually we commented on the stability status of the system. That was our target. Right. Somehow again we have to come back to our time domain response, right? So this is the graphical approach, but we do not know the mathematical value, right? That's why we want to now formulate the del delta, okay, in time domain. Okay. So now we want to know this del delta value in time domain. Okay. Obviously with respect to other parameters, not like this, because in this thing you can find the del delta. Okay. It will be difficult for you. we want to express this del delta with some other parameters so that we can easily calculate this force. Also, we want to know the del omega of t. Okay, we want to know this one because these two is our state variables, right? Because for this linearized swing equation, we know that this del delta and del omega, these two, this one and this one is our x1 and x2. These two are the state variables. So we want to know the time domain response of these two. Okay. Now we have to apply the inverse Laplace, right? So that will we will now continue the discussion of inverse Laplace transform response. And finally we will find out the del delta of t and del omega of t. So now we want to start from this slide. So this is our input equations, x1 dot and x2. Now we can also formulate the output equations, right? So let's say our output vector is y. Okay. Let's say there are two outputs, okay, x1 and x2. So how we can write the output equation? Simply inside y it will have x1 and x2 like this, right? So that means again this y is equal to cx plus dt, right? So we know that in the input equation we do not have any du term, that is there is no forcing function here. That's why also in this output equation there will be no du. So only there will be y equals to cx. So in this manner we have to form the matrix. So this is our x, here x will be x1 x2 and our output is also x1 and x2. Okay, we are just assuming this thing. Okay, because this is just for your understanding, we are not bothering about the outputs. Because you will see that after this topic we will just try to find out the value of our state variables del delta and del omega. Okay. For this output equation it is just to actually make the things clear to you how actually we can find out the output equations. So now if this is x, so what will be our c? We can easily find it, right? Because inside 1 the size is 2 by 1 and this x size is also 2 by 1. So what should be the size of this C matrix? It should be 2 by 2. And how we will put the entries of this C matrix? So your y is x1 and x2. So it should be 1 and it should be 2. And it should be 0 and it should be 1. So that you can get the x1 for the first element and x2 for the second element. Okay. This is very much simple. So this is the C matrix. Now let's go to the Laplace transform again for this state equation. Okay. So now we will actually try to apply Laplace transform for this state equation. Then we will apply the inverse Laplace transform to find out the del delta of t and del omega of t. Okay. So if we apply the Laplace transform here in this expression, okay, here our expression is homogeneous state equation or unforced state variable equation, right? If we apply the Laplace transform, okay, so what is our expression? X dot equals to ax, right? This thing. So we know if we do the Laplace transform of this term, what will be it? So this is nothing but dx over dt, right? So the Laplace transform of this term will be simply s then multiplied by x of s, because now this x is in the frequency domain, by the s domain. Then there should be one additional term, that is x. Why? Because this is the initial condition. Because in this system we do not have any input. So how the system will operate? There should have some initial conditions, right? Actually I gave the example of this circuit. Let's say we do not have this VA in our system. So how the system will operate? The system will operate only that time whenever there are some stored charge inside this capacitor and this inductors. Okay. At that time only the system will work. So we need some initial conditions because we are considering the unforced response. Okay. There is no zero. input, that means zero input response, right? That's why there should have some initial conditions. That's why this is important. We have to add this initial condition here. Then again, for this term, what will be the Laplace transform of this term? A is constant, so A will remain as it is, and for this x we will get x of s, right? Should we add the initial condition here in this side? No, because the initial condition comes only with the derivative term, right? I think you know this thing. So this is our Laplace transform for this expression. Now we are just rearranging this equation like this. This term is in the right hand side, so it will be plus x of 0, and this has come to the left side. Okay. Now if you take common of x of s, then you will get s minus a, right? Because here it is s, and from this a you will get a. But why I is here? What is I? Identity matrix. Why we have placed I here out of nowhere? Exactly. So S is actually x scalar, right? But this A is matrix, and for this case, our A is a 2 by 2 matrix, right? So S is scalar. So somehow we have to match the size of this two term so that we can subtract, right? That's why we have multiplied I. I means the identity matrix, and the size of the I will be exactly same as the A. Okay, so it will also be the 2 by 2 matrix. Now we want to find the x of s. So what will be the x of s? If you just take this term here, as this is the matrix. So if we take it to the left right side, it will be simply inverse, right? So inverse of this matrix multiplied by x of 0. X of 0 is the initial conditions for the state variables. Okay. Now what is I here? I is a 2 by 2 identity matrix. So what will be the s like? This will be simply s multiplied by 1. So there will be s and there will be s, right? And what will be si minus a? We know the A matrix, right? What is A matrix? This one is the A matrix, right? 0, 1 minus pi f naught ts over h minus pi f naught t over x. Okay. So look, this is our A. So si, this is si minus a. Okay. So if you do the subtraction, you will get s. Here you will get minus 1. So 0 minus will be plus. It will be pi f naught ts over h. For this term, it will be s plus this term. Okay. So do you have any confusion here? Alright. We can move forward. So this is our.
You mentioned that we have to use the initial condition with derivative. So what it is to এটা সম্পর্কিত আপনি বলবেন আমি
So this is the property of Laplace transform. Okay. Whenever you will do the Laplace transform of this thing. This is a time domain parameter x1 of t, right? So you can simply write x1 of s. There is no need to add additional initial condition. Okay. But whenever it is x1 dot of t, that is the first derivative of this t. Actually this is nothing but dx1 of t over dt, right? So the Laplace transform of this term will be s x of s, and you have to add the initial condition. This is the formula that we do.
It is the inherent property.
Okay, yeah, this is inherent property, but you can try to understand this thing by your own method. Okay, there also has some physical meaning. How actually this thing is added with this derivative term and not with this thing. Okay, so try to find out this answer, okay, by your own. Okay, so this is the Laplace transform property, but obviously there is some reasoning why it is like minus x of 0, why we are adding the initial conditions. So this is now si minus a. Look. So this is nothing but the omega n square. Okay. How? Look. So in one of our previous lectures, we actually found out the omega n square. So look, pi f naught ds over s, right? The same equation, same linearized swing equation with derivative. So omega n square is pi f naught ds over s, and this term is 2 g zeta omega n. Okay, so that's why we can replace this term with omega n square. This is omega n square and this is actually 2 zeta omega n. Okay, now what will be the inverse of this 2 by 2 matrix? So it is very easy, right? So for 2 by 2 matrix, you can just interchange these two elements, right? This will be here and it will be here. And for these two of diagonal elements, you have to just change the sign, right? There is -1, it will be +1, and for omega n square it will be minus omega n square. And obviously you have to divide this by the determinant of this matrix, right? What is the determinant? So if you multiply these two, it will be s square plus 2 zeta omega n s, and for this minus plus, so plus omega n square. Okay, so this is the determinant. So now what will be the x of s? Look, x of s is the inverse matrix of si minus a multiplied by the initial condition. Okay, so this is the si minus a inverse and this is x of 0. Okay, now actually what is x of s? What is inside this x of s? Okay, we have two state variables, right? Del delta and del omega. So inside this x of s we will have actually del delta in s domain and del omega in s domain. Okay, this is actually inside this x of s. Do you have any question here? Why actually inside this x of s we have these two? Because previously we determined our state variables. Okay, it was x and it was actually del delta and del omega, right? Del omega or t del delta of dt, the same thing. This is actually del omega. This is in the time domain, but whenever we are applying the Laplace transform, so this should be in the frequency domain or in the s domain. So this is del delta of s and this is del omega of s. Okay, and the right side is same as it is, but what will be the initial condition? Again the x of 0. So inside this x we will have two elements, del delta of 0 and it will be del omega of 0. Okay, and now this thing. Now we will consider that. Okay, so there is one point here. These two initial conditions, okay, at least one must be non-zero, right? Because if these two are 0 at that time, how the system will operate? Because for this system there is no input, there is no forcing function. So there should have at least one initial condition. Either this should be non-zero or this should be non-zero, or both can be non-zero, but both can't be 0. Okay, that is the case. So for this case, as we are discussing the small disturbance stability, so we are applying some disturbance in the rotor angle, right? And that will be experienced by this del delta. So we can say that the rotor is suddenly disturbed by a small angle, so we will have some non-zero of del delta at the initial stage, right? So this is the initial condition. So we will assume that our del delta of 0 actually is not 0. So this is a non-zero quantity, but we can take our del omega of 0 as 0. Okay, because we can say that this change is very small, that actually the change in the angular speed is can be assumed as 0. Okay, because this is related to this. So if this is non-zero, this should be non-zero. But as the change is very small, so we are assuming this thing, that we are assuming that our del omega of 0 is actually 0. Okay, actually we are following the textbook and we are following the chapter 11. Okay, you will find all of this thing in your chapter 11 of the textbook that I share. Okay, so you will see that in the textbook the first case is we are considering this del delta of 0 as non-zero and del omega of 0 as 0. Now here this term will be here, but this term will be 0. Okay, now what will be the del delta of s? Simply this multiplied by this divided by this, right? So just try to understand this thing. What will be the del delta of S? There will be some matrix multiplication, right? Look, this is matrix, this is matrix, and this is, let's say, some constant term in the denominator. Okay, so this multiplied by this plus this multiplied by this, but this is already 0, so it will be simply S plus 2 zeta omega n multiplied by del delta of 0 divided by this. Okay, that will be your del delta of S. Look, this is your del delta of S. S plus 2 zeta omega n multiplied by del delta of 0 divided by this term. And what will be the second element, that is del omega of S? It will be this term multiplied by del delta of S. If you multiply this with 0, it will be 0, so only this term will be left, that is minus omega n square multiplied by del delta of 0 divided by this. Okay, so look, this is this. Okay, so have you understood how actually we have found these two? The assumptions are this. This is not 0, but this is 0. Okay, and now we can move forward. Okay, now we have to apply the inverse Laplace for this del delta of S and del omega of S. What will be the inverse Laplace of this del delta of S? It will be del delta of t, right? That is our target to find out. Now, before applying the inverse Laplace directly, we can just rearrange some terms, okay, so that we can follow the Laplace transform and inverse Laplace transform tables, right? We have some tables for Laplace transform and inverse Laplace, right? If you can make make any term compatible with that table, then you can directly use that formula, right? So that's why this is del delta of S, but there is no thing, you will not find this type of thing in the tables. Okay, that's why you have to change this thing, or you have to rearrange this thing so that it can be compatible with your Laplace transform table, so that it can be represented by the form. Okay, so look how it is done. From this line to this line, there is S plus 2 zeta omega n, right? So you can split this 2 zeta omega n by zeta omega n plus zeta omega n, right? So one zeta omega n is here, that is S plus zeta omega n, and another zeta omega n is here. Okay, and obviously with the plus sign, and in the denominator it is S square plus 2 zeta omega n s plus omega n square. So this, but we have added zeta square omega n square, so you have to subtract the same term here. Okay, so this is, so this will be cancelled out, and you are getting the same thing, S square plus 2 zeta omega n s and this omega n square. Okay, similarly here as well, look, plus zeta square omega n square minus zeta square omega n square. Okay, now from this line to this line, how we can write? Okay, the change is in the denominator. So look, this term you can write it like S plus zeta omega n whole square, right? And this term you can write, you can take omega n square common, and it will be 1 minus zeta square. So the same is here. Okay, now you can write it like this. So look, this is S plus zeta omega n square, and here as well it is. Okay, look, this term, this is square, and here if you place root over here, it will be also square. Okay, see, it is written like omega n root over 1 minus zeta square whole square. Okay, and in this term, the second term, this is zeta, so this zeta has come here. Okay, and you have multiplied root over 1 minus zeta square in the upside and in the downside as well. So these two will be cancelled. The same thing you have multiplied in the numerator as well as in the denominator. So it will be same. Okay, and for this thing it is S plus zeta omega n whole square, and for this thing it is omega n root over 1 minus zeta square whole square. Okay, so have you understood up to now? Have you omega n is equal to a, and omega n root over 1 minus zeta square is your b. Okay. Now what will be this equation? It will be simply s plus a, right? And in the denominator it will be s plus a whole square plus b square, right? And it is del delta of 0. For this case it will be like this, the same thing, zeta over 1 minus zeta square, and this term is nothing but the b, and in the denominator it is s plus a square plus b square, right? And del delta of 0. Okay. Now can you relate this thing with your Laplace transform table? What will be the inverse Laplace of this thing? It will be, can you remember what will be the inverse Laplace of this thing? It will be simply e minus at cos bt, right? And for this thing it will be e minus at sin b. Okay. Look, now we will apply this formula. So we have done all this rearrangement just to make this thing compatible with our Laplace transform. Okay. Now we will apply the inverse Laplace. Look, this is the inverse Laplace. So it will be e to the power minus at. What is a? A is the zeta omega n, right? So I am writing the same thing here. The assumption is zeta omega n is a and omega n root over 1 minus zeta square is b. So our zeta omega n is equal to a and omega n root over 1 minus zeta square is equal to, okay. So e to the power minus at cos b, okay, plus this is the constant term, this term that has come here, okay, and for this term you will get e to the power minus at sin bt, okay, and there is del delta of 0, okay. Have you understood this thing? Is there any confusion here? Now this is nothing but your omega t. Can you recall what is your omega t? Damped frequency of oscillation. Omega n is the natural frequency of oscillation. What is the relationship between these two? Look, what is your omega t? Okay. Omega t is equal to omega n root over 1 minus zeta square. Okay. That's why if you are replaced this term with omega t. Okay. So this is cos omega t, this is sin omega t. Okay. Now you can take this term common, that is e to the power minus zeta omega n t over 1 minus zeta square. Okay. So you will get this term here because it is being divided here. So you will get it here by multiplication term. So it will be root over 1 minus zeta square cos omega dt plus here this zeta sin omega dt. Okay. And this is del delta of 0. Now here we have to use a trick. We have to use a right angle triangle. Okay. So let's say this is our right angle triangle. Okay. So this is the base. Okay. And this is the vertical arm and this is the hypotenuse. Okay. So let's say this is the theta. Let's say the size of the base is zeta and the size of this vertical arm is root over 1 minus zeta square. Okay. So what will be the value of our hypotenuse? It will be root over this square plus this square. Simply it will be root over 1 this 1. Okay. Now what is, by looking at this right angle triangle, and you have the sizes of 3 arms, okay, of this triangle, can you write the cos theta formula? It will be simply this base divided by the hypotenuse, that is theta over 1, simply theta. And what will be the sin theta? It is this vertical arc divided by this hypotenuse. Okay, it is root over 1 minus theta square. Now we can replace this root over 1 minus theta square with sin theta and this theta with cos theta. Look, this is our sin theta and this is our cos theta. Okay. But obviously you have to remember the theta. What is theta? You have to calculate it. What is theta? Theta will be cos over theta. Okay. Or it will be sin inverse root over 1 minus theta square. You can use any of this equation to find the theta. So now it is sin theta cos omega dt plus cos theta sin omega dt. Now we can apply the formula, right? The trigonometric formula. It is nothing but the sin a plus b. So it is sin a is omega dt, b is theta. Okay. So now we are getting this thing. Look, this term is coming in the first. Okay. So this is del delta of 0 e to the power minus zeta omega nt root over 1 minus theta square sin omega dt plus 0. Okay. So this is your del delta in the time domain. Now if you have the value of this, the initial conditions as well as the zeta and the omega n, you can find out the del delta and you can plot it in the graph just with the time. Okay, then you can see the response. Because to plot this type of graph, you need the initial values as well as the final values, right? Otherwise you can plot it randomly. Okay, so you need these values, you need the final values, you need the stable values like this. Okay, so that's why we are finding, or we are actually trying to get the time domain value of our del delta. Okay, so do we have any confusion up to now? No, right? Any confusion? Actually, I have tried from my side to actually make the things clear to you. I have shown you all the steps. Okay. In the book, you will see that this line has been written, and directly they have written this line for this inverse Laplace transform. This line. Okay. And the intermediate steps are given here. Okay. You can follow these steps. Actually understand these things more better. Okay. Now let's go to the del omega of s part. This part. Okay. This thing. So this is del omega of s. Now again you have to rearrange this thing, but this should be easy to read because there is only one term. Okay. This term we have dealt this term here as well. Good. This is nothing but this type of term. Okay. So you can easily deal with this term. How? So this is your del omega of s. So we have written here omega n and this is minus omega n. So it will be minus omega n square. So we have just put root over 1 minus omega square zeta square in upside and as well as in the downside. Okay. And here the same thing, plus zeta square omega square minus zeta square omega square. Okay. So look, this is your b, this is your a. So s plus b over s plus a square plus b square. Okay. This is the formula. So what will be the inverse Laplace transform? It will be e to the power minus at sin bt. Okay. So sin bt. Now again this is actually omega t. This is sin omega dt e to the power minus zeta omega nt, and this term for this constant term as well as for this. Okay. So I think you have understood this thing as well, right? This is your del omega of t. Okay. Now we have actually determined the del delta of t and del omega of t. Okay. Now can we actually go back to the del of t and omega of t from these two values? What should be the relationship between this del delta of t and delta of t? It should be delta of 0 plus del delta of t. Right? Can you recall? Get some previous lectures. This was our first assumption. We replaced the delta with delta 1 plus del delta. That's why the del delta term is actually here. Now again we have to go back to this delta. Okay. So what will be our delta value now? It should be the del delta of t plus some initial condition. Okay. So look this one. Now what is the delta of t? This is delta of 0, the initial condition, plus this is actually your delta of t. That okay. What will be the rotor angular velocity omega of t? It will be omega of 0 plus del omega of t. But in this del omega of t we have some minus sign. That's why this minus has come here. Okay. This is nothing but omega of 0 plus del omega of t. Okay. And in the del omega of t we have some minus now. That's why this is minus. Okay. And this response is called zero input response. Do you know why this is called zero input response? Because we didn't have any input, right? We didn't have any forcing function. So this is zero input response, or actually the unforced response. Okay. Now we have to solve the example 11.2 from the book. So actually there are two examples, 11.2 and 11.3. So we will solve these two examples in the next class. But before that, I want to cover few more slides. Actually, all the slides I will cover today. Okay. So we are now here. We have completed the formulation of zero input response or the unforced response. Okay. Now let's go to the forced response. So what is called by the forced response? Whenever there will be some forcing function or input, at that time the response will be called as forced response. Okay. Now look, we will now investigate the system response to small power impacts. Okay. So assume that the power input is increased by a small amount. Okay. Actually, as this is the PDF file, so in the PowerPoint file that I will share with you in the whole classroom, you will see that there is actually delta del PM. Okay. This is actually del PM. The change in the mechanical power input. Okay. Now we are actually creating some difference or creating some change in the mechanical power input, and that is expressed by this del PM. Okay. Now obviously this is some external factor, right? So now this will act as the forcing function, and now the response that we will try to observe, that will be the forced response. So have you understood up to now why actually this is called forced response and why actually we are introducing this del PM? So with this del PM, our updated linearized swing equation will be like this. So this was the previous case with del P. It was equal to 0, but as there is some disturbance, so it will be equal to 0. There will be some change here. Okay, it will be del PM. Okay, because previously it was PM minus PE, and there was no change. That's why it was actually 0. Okay, but now there is some change in the mechanical power input. That's why it will be del PM. Now look, we have just divided this term. Okay, in both sides. That's why today the coefficient of this term 1. Okay, that's why we are getting this type of things. Okay, I think you can understand this line from the previous line. Okay. Now in terms of the standard second order equation, now this will be our standard second order equation. Okay. There will be some del U. Okay, because there is some input here, and this is the second order derivative. It should be the 2 zeta omega n d delta of t, and omega n square del delta equals to del A. Okay, I think you have studied this thing in your control system engineering course, right? This type of system with Lego. Okay, so, and here we are considering the step input. Okay, step input. That means the response that we will get the step response, and obviously this is due to the forcing function, or actually this is the forced response. So let's say this is the input response. So now again we have to actually first, in the first step we have to determine the state variables. Okay, so how many state variables will be there? 2. As this is the second order system. So look, the first one will be this del delta, the second one will be del omega. Okay, and what will be the x2 dot now? So this is our x2 dot. It will be simply this term will be in the right side. So it is this plus del u, then omega n square. This is nothing but the x1. That's why this is x1, and this is 2 zeta omega n, and this is actually the x2. Okay, so this is your x2. You can easily understand this thing if you understand the previous topic, then this should be very easy to you. Okay. Now we have to form this in a matrix. So this is our matrix form. This is x dot. This is now ax. Not only x, rather we have the b here as well. Okay. Previously we had only ax. That was the natural response of the unforced response. Here into this is called the forced response. Okay. You can easily formulate the matrix. Okay. I am not showing this thing. You can do it by observing these two equations. This equation and this equation. Okay. So this is like x dot equals to ax plus b del u. Okay. And this is called the forced state variable equation. And another name is zero state equation. Why zero state? Now in this case we will consider that our delta of 0 and del omega of 0 is actually 0, because we do not need any initial condition. Okay. We will neglect the initial condition and we will make these two things equal to 0. Only we will consider about the forcing function that is coming here in terms of this del. Okay, so that's why this is called the zero state equation. Now if you take x1 and x2 as your output, then that will be your output equation. That will be simply Cx. Okay, there is no plus du term. Now again we have to apply the Laplace transform for this scenario. Okay, so if you apply the Laplace transform here, what you will get? You will get s x of s. Is there any initial condition here? No. So you should not write this. On this side it will be a x of s. And for this b is the constant. We will have the u of s. Okay, or del capital U of s like this. Good. This is the okay. Now I have mentioned that we have assumed that our del u is a step response. Okay. Del u it is in the time domain. Okay. But this del capital U of s it is in the s domain. So what will be the relationship? That means if we do the inverse Laplace of this term, we will get this over this, right? And remember inside your Laplace transform table for the input response or for the step response or for the step input, you actually get this type of thing, right? If your input is step type, then it is simply this over this. This is the inverse Laplace transform. So if you do the inverse Laplace transform of this del capital U of s, you will get del u over s. Okay. So this is simply the formula of your inverse Laplace transform. Now, look, what will be your x of s? You can just take this term in the left side, and you can take x of s common, then you will get si minus a. Again, bring that si minus a in the right side, then you will be the inverse. Okay. You know this well. It's the same si minus, right? So you will get this. This is the thing. So and this is simply del u over s, as this is a step input. Now from here, inside this x of s, again we will have two things. One will be del delta of s, another will be del omega of s. How we will find the del delta of s? By multiplying this with this, right? So this is 0, so only this term will be here, 1 multiplied by del u. So that's why only del u, and this is the denominator term like this. And we are just taking there is s, yes, that's why there is s. And for this del omega of s, you have to just multiply the second row with this thing. So for this will be multiplied, okay, and this s will be cancelled out. That's why only this del u over this. Okay. Now again we have to apply the inverse Laplace. Okay. So let's say by applying some we are rearranging this thing like this. Then if we apply the inverse Laplace, you will get this. Okay, I am not showing this thing. You should know this thing. Okay, because I have shown the one case step by step. Okay, or line by line, and this thing you will easily understand. Okay, so this is nothing but your inverse Laplace transform. Okay, and if you follow the inverse Laplace transform table, you can easily get this thing. Okay, and this is real omega of s. Again, you have to do some kind of rearrangement, and finally, if you apply the inverse Laplace, you will get this. Okay. Now, this is obviously for your force response. Okay. Now, again, go back to your delta of t. It will be delta of 0 plus del delta of t. You know this thing from the previous case. And what will be your omega of t? It will be your omega of 0 plus del omega of t. Then you will get this. Okay. And obviously, this is called the zero step response. Why? Because there is no initial condition for the step variables. Okay. Yeah, that means here our del omega 0 is 0, not this is 0. Okay. This is omega of 0. And we are assuming that our step variables were del delta and del omega. The initial condition of these two step variables we are assuming as 0. Okay, that's why this is called the zero step response. And previously it was the zero input response. So zero input response is for the unforced case, and the zero step response is for the forced response. Okay. Have you understood this thing? Now again there is another example, 11.3. So 11.2 and 3 I will solve it in the next question. Okay. And that will actually be the end of this slide. And then we will start a new slide. Okay. That will be the large disturbance system, the transient stability. Yes, so try to go through this slide. Actually, it was better if actually I had the opportunity to actually to take some quizzes of it. Okay, at that time you will read the slide. Otherwise, if I ask you read it, actually you will not read it until the semester. Okay, that's the thing. So what I can do, okay, because you know that there is no mark for quizzes. Okay, so still if I take some dummy quizzes, you will not take because there is no marks for the quizzes.